this lecture, we'll begin our exploration of everyday engineering by focusing our attention on one particularly important technological system that quite literally surrounds us in our daily lives. For the next 4 lectures, we'll be examining your house, first as an engineered system in its own right, and then in its broader technological context as one component of the extraordinary system of systems comprising our civil infrastructure. And then I'll conclude by introducing you to the rather unlikely hero of this story, the regulatory document that governs the safety, economy, constructability, and efficiency of residential construction throughout the US, the Building Code. But can a simple residential dwelling really be characterized as an engineered system? Well, you might not think about it this way, but yes, absolutely. As we shall see shortly, a well-designed, well-built, and well-maintained house actually provides a rather impressive array of technological functions. These functions are fulfilled by an integrated assemblage of 8 major building subsystems, the design of which implies a very high level of engineering sophistication. The structural system supports the weight of the building itself, the weight of snow and ice on the roof, the occasionally severe environmental loads caused by wind and possibly even earthquakes, and the weight of people and their accumulated stuff, furniture, appliances, clothing, books, pots and pans, you name it. The building envelope is a highly specialized set of building components that keeps the elements out and helps maintain an appropriate range of temperature and humidity inside, while also allowing for access, egress, and natural illumination. The foundation is, in one sense, part of the structural system because it transmits the weight of the building and other loads safely down into the earth, but it also serves as a critically important component of the building envelope, protecting the home from groundwater infiltration and heat loss, and sometimes enclosing additional living or utility space as well. The heating, ventilating, and air conditioning system, abbreviated HVAC and usually pronounced HVAC, provides control of temperature and humidity while also supplying fresh air. The electrical system provides electrical power to outlets, light fixtures, appliances, air conditioning, perhaps heating, and various control systems like the thermostats that control both your HVAC system and your hot water heating. The plumbing system delivers fresh water under pressure to various fixtures throughout the building, and it removes wastewater from these same fixtures. The telecommunications system includes phone, cable, and wireless links that enable the transmission of information to and from the outside world. Now, until recently, your home's built-in telecommunications might have included nothing more than a telephone line and perhaps a cable TV hookup, and could hardly have been characterized as a system. But today, with the advent of in-home computer networks, satellite TV, internet-enabled climate control, and who knows what next, the private residence has truly become a telecommunications hub. Finally, a vital yet often overlooked subsystem is your building site, the plot of land on which your home is situated. The building site provides structural support for your foundation. It controls the flow of storm water across the site. It connects your residence to the local road network via your driveway and to public utilities via curbside connections. We'll look at each of these subsystems in considerably greater detail in future lectures. But for now, it's most important to see them from the macro perspective as highly integrated components of a far greater whole. Now, when I say that these building subsystems must be integrated, I'm actually referring to 3 distinctly different aspects of residential design and construction. First, those 8 subsystems, structural, building envelope, foundation, HVAC, electrical, plumbing, telecommunications, and site, must work with each other. Second, they must work within the context of a broader architectural design. And third, they must be integrated within large-scale civil infrastructure systems. Let's consider each of these 3 forms of design integration in greater detail. First, subsystems must be integrated with each other. The 8 building subsystems are highly interdependent. Consider a few common examples. Your water supply lines, wastewater pipes, electrical wires, telecommunication cables, and air conditioning ducts must all pass through structural wall framing and floor framing without adversely affecting their load carrying capacity. In this photo, we see water supply lines and wastewater pipes integrated within the structural framing of a typical house. Your plumbing system depends on your electrical system, which powers the hot water heater and the garbage disposer. If you heat your home with water circulated through baseboards, then your heating system depends on your plumbing system for its water supply. Your heating and air conditioning systems also depend on your electrical system, even if you heat with oil or natural gas, because the electrical system powers the thermostats, fans, and compressors that the other systems require. The effectiveness of your heating and air conditioning system is also highly dependent on certain characteristics of the building envelope: its air tightness, the amount and type of insulation, the sizes and types of windows and doors. Now, the second form of design integration is that the 8 subsystems must work within the context of an overarching architectural design. Typical elements of an architectural design for a residential building include the allocation of interior space to various rooms and functions, defining how large each room should be. Access and circulation, defining how occupants will enter, exit, and move around within the home. Adjacencies, defining which rooms should be close together and which should be far apart. Fenestration, defining the sizes and locations of windows. The locations of major appliances and fixtures. And of course, aesthetics, which includes the house's overall style and form, its position on the building site, and its exterior and interior materials, finishes, and details. Now, from the perspective of the typical home buyer, all of these architectural elements are probably more important than any of the engineered subsystems. This is the case, at least in part, because the engineered systems are largely hidden from view, out of sight, out of mind. But also because we tend to assume that these systems are well designed and working properly unless we see clear evidence to the contrary. For these reasons, home buying decisions are far more likely to be made on the basis of architectural rather than engineering criteria. And consequently, the underlying engineering design of any building, private or commercial, is almost always subordinate to the architectural design. The engineered subsystems must accommodate the spatial and aesthetic demands posed by the architecture, not the other way around. For example, if the architectural design calls for an open floor plan with few interior partition walls, as you see here, the structural design may need to provide for unusually long-spanning beams to support the ceilings, and the electrical system might include a lot of floor-mounted outlets. If the architectural design calls for an exterior wall of glass, the structural, heating, and building envelope systems will have to accommodate the unique demands associated with this architectural feature. Third form of design integration. Unless you're living in a log cabin in the wilderness, your house is embedded within a large, complex network of civil infrastructure. Now, the term infrastructure refers to large-scale technological structures and systems that enhance societal functions, facilitate economic development, and enhance quality of life. The most important elements of civil infrastructure are transportation, electrical power, water supply, wastewater disposal, stormwater management, and telecommunications. As you can probably see, each of these major infrastructure networks has one or more interfaces with the engineered subsystems of your house. Our civil infrastructure is a technological system of systems, the scope and complexity of which is nothing short of mind-boggling. Yet we must devote the time and energy necessary to understand it, because the everyday engineering we experience inside our homes would simply be impossible without it. To help us wrap our brains around the civil infrastructure, I'd like to try depicting it graphically, albeit in greatly simplified diagrammatic form. There are many, many possible variations in this diagram, depending on, for example, whether your residence is a single-family home or an apartment in a high-rise tower, whether your heating system is an oil-fired furnace or an electric heat pump, whether your wastewater is discharged into a public sewer system or an on-site septic tank. For the sake of simplicity, I'm going to depict the infrastructure connections associated with my own home, and I think you'll see that your situation varies from mine in relatively minor ways that don't substantially alter the big picture. And a big picture it shall be. Here's my house with its structural system, foundation, building envelope, and site. And inside, it's HVAC, electrical, plumbing, and telecommunications subsystems. My house has 8 major connections to local and regional infrastructure. Let's examine each one. First connection is electrical power, which serves as input to my electrical system. My power comes from several different sources, but for the sake of simplicity, I'll depict just one, the largest contributor, the chemical energy of coal. Vast quantities of this material are extracted from the earth at a coal mine. The coal is cleaned and sorted at a processing facility, and then loaded onto a freight railroad for transport across an extensive track network to a coal-fired power plant. This facility burns coal to produce steam that drives a series of turbines, which spin the generators that produce electric power. This electricity is then fed into an extensive regional power grid, consisting of a vast network of high-voltage transmission lines which can move power efficiently over long distances, substations which lower the voltage to safer levels for transmission over the last few miles to my house, and low-voltage distribution lines supported on the wooden power poles that are such a dominant feature of our modern landscape. And this brings us back to my house, where a single line called a service drop supplies me with both 120 volt and 240 volt power. And what about the natural gas that fuels my furnace and my hot water heater, not to mention many power plants? Well, it originates in an underground deposit that's tapped by a drilling rig, then extracted from a well, piped to a gas processing plant, where it's cleaned and refined, and then sent through a complex transmission and distribution system consisting of compressor stations, gates, and pipe networks to commercial and residential customers like me. My third infrastructure connection is fresh water, which supplies my plumbing system. This resource originates in a local reservoir created by building an earth dam across the stream. Water is drawn from this reservoir, purified in the adjacent water treatment plant, and then pumped into a storage tower located on a hilltop at the edge of town. From the tower, water mains loop through my neighborhood, and a single supply line extends from one of these mains into my basement. Most of the fresh water that enters my home through this supply line eventually leaves as wastewater. Every household fixture that supplies water also has a means of collecting wastewater and channeling it through my plumbing system into the local municipal sanitary sewer system. The only evidence of this system I can see is that manhole cover in the street at the bottom of my driveway. But beneath the street, an extensive network of concrete sewer pipes collects and carries the wastewater on a gradual downhill slope to my local wastewater treatment plant, which purifies the water in a complex 3-stage process and then returns it to a local stream. The other form of water infrastructure that supports my home is the one that kicks in whenever it rains. This precipitation is directed off my roof, captured by my gutters and downspouts, and deposited in my yard and driveway as storm runoff. This flow of water is guided by the contours of my yard and driveway down to the street, where it enters the municipal storm drainage system. This system captures and transmits storm runoff and melted snow through an underground pipe network into a local stream. The other infrastructure system designed to get undesirable stuff out of my house begins with me, carrying bins of food waste, milk cartons, packaging, aluminum cans, glass bottles, newspapers, and who knows what else down to the curb. Here, the solid waste, often imprecisely characterized as garbage, is loaded into trucks and hauled either to a local landfill, where it's returned to the earth in an environmentally responsible manner, or to my municipal recycling center, where it's processed for reuse. My driveway also connects my home to a vast highway infrastructure, ranging from local roads to major limited access highways called arterials that facilitate long-distance travel. This system also incorporates an incredible variety of bridges, intersections, and traffic control technologies designed to keep traffic flowing smoothly while minimizing the probability of crashes. Finally, telecommunications. I'm a low-tech guy, so my house's sole built-in telecom link to the outside world is a simple landline telephone. Simple, yes, but through its interface with my local telephone exchange, this modest pair of twisted copper wires can connect me to any landline phone on the planet through a system called the Public Switch Telephone Network, or PSTN, or with any cell phone on the planet, if necessary, through an interface with a satellite in orbit. And through my digital subscriber line, or DSL service, the same twisted pair can simultaneously transmit digital information to and from the farthest reaches of the internet. If ever there was an underappreciated piece of everyday engineering, this is it. These connections to our civil infrastructure are absolutely integral to everyday engineering, and so we'll be examining all of them in greater detail throughout the course. For now, I think it's important just to appreciate the overall character of this amazing system of systems, its extraordinary scope and complexity, its interconnectedness, the diversity of technologies contained within it, and its dynamic, ever-changing nature. And at the heart of this amazing system is my house and yours. But how is this technological marvel realized? How is a residential building designed such that its subsystems are integrated with each other and with this complex web of civil infrastructure systems? Perhaps surprisingly, the answer is not an engineer does it. In the US, individual private homes are usually designed by developers or builders, sometimes by architects, but hardly ever by engineers. So how could this complex technological entity that I've been describing as an engineered system not be designed by engineers? I can answer that question in two simple words: building codes. A building code is a set of rules specifying minimum standards for construction. Its principal purpose is to protect public health, safety, and welfare, though modern codes also promote such secondary concerns as economy, constructability, and sustainability. Historians attribute the invention of the building code to King Hammurabi of ancient Babylon. Indeed, Hammurabi's code of the 18th century BC includes a series of provisions like this one. If a builder builds a house for someone and does not construct it properly, and the house which he built falls in and kills its owner, then that builder shall be put to death. Well, that's a pretty good incentive for construction quality, but it doesn't do much to inform the builder about how he might avoid a structural collapse. Modern codes have adopted a significantly more prescriptive approach by adopting technological standards aimed at preventing particular types of failures from happening. Not surprisingly, these initiatives to expand the scope and technical demands of building codes typically followed large-scale disasters, like the Great London Fire of 1666, the Great Chicago Fire of 1871, the San Francisco earthquake of 1906, and Hurricane Andrew in 1992. The 20th century saw three important trends in the development of building codes. First, as engineering knowledge expanded at an ever-increasing rate, the associated codes became ever larger ever more complex and ever more prescriptive. With each new building failure or new research finding, code provisions were added to address the underlying issue. At the same time, building codes became increasingly balkanized, with wide variations in standards across regions, cities, and municipalities. In part to address these problems, responsibility for code writing in the US gradually passed from governments to nonprofit professional societies called standards organizations, which could claim national or international scope while also commanding the high-level technical expertise necessary to develop codes reflecting current best practices. And because these standards organizations had and still have no legislative authority, they instituted that system of model codes that remains in use today. Now, a model code, in essence, is the consensus recommendation of the professional community represented by a particular standards organization. For example, the American Concrete Institute publishes a model code governing the design of concrete buildings. But that model code has no legal status, and it's not enforceable unless it's formally adopted by a government entity, typically a state, county, or municipality, through legislation. Although the development of model codes was quite beneficial, US building codes were still a mess until quite late in the 20th century. At that time, 3 major standards organizations were promulgating 3 independent model codes, and adoption of these codes across the country was haphazard at best. But that situation changed dramatically in 1994 when these 3 organizations merged to form the International Code Council, or ICC. By 2000, the ICC was publishing the first true national building codes in the US. The ICC is a professional society composed of technical experts, industry representatives, and regulators who work collaboratively to develop 15 interrelated and complementary model codes, including the International Building Code, the International Energy Conservation Code, and the one we'll be working with in the next few lectures, the International Residential Code. ICC codes are developed and updated through a structured and highly participatory process implemented on a regular 3-year cycle. Anyone in the world can submit a proposed code change, and hundreds are considered during every 3-year change cycle. Over time, as model codes have become increasingly standardized, more governmental jurisdictions have been willing to adopt them through legislation. And this just makes sense. After all, code writing is a complicated business requiring considerable time and technical expertise. Why not hand this process off to the professionals? Moreover, widespread adoption of standardized model codes is highly advantageous to builders and developers who work in multiple political jurisdictions. Imagine trying to build houses according to several different sets of rules simply because the houses happen to be located a few miles apart. So what does all this have to do with the fact that your house probably wasn't designed by an engineer? Well, residential construction directly affects a huge proportion of our population, and there's strong popular desire to keep housing costs as low as possible. As a result, over the past century, the model building codes have standardized and institutionalized residential construction methods at such a high level of detail that the codes can effectively serve as a substitute for an engineer's design. Now, later in the course, we'll work through the design of a floor beam in your house using the International Residential Code. And you'll see that the process is quite like following a recipe in a cookbook. Just follow the step-by-step procedure, select the required beam size and material specifications from a table. No calculations required. As long as your house uses a standard structural configuration, there's very little room for discretionary judgment in this process, and thus no real need for a professional engineer. Now, that's why in most US jurisdictions, there's no legal requirement for an engineer to be involved in designing a private residence unless the structure has unusual features like unusually long beam spans, unusually heavy loads, large wall openings, or unconventional building materials, conditions that are not addressed in the cookbook. Otherwise, the builder is simply required to comply with the code. Now, having said that, it's also important to recognize that engineers are indirectly involved in the design of even the most conventional house because engineers contribute extensively to writing the model codes. These codes always incorporate substantial engineering research performed in universities and in corporate product development shops, as well as engineers' collective experience with the in-service performance of existing structures. Thus, a builder who complies with a code is effectively implementing a thoroughly engineered design. The downside of this process is that new engineering research and new technologies are emerging every day. Many of these developments are eventually incorporated into codes, while hardly anything is ever removed from codes. The result is quite evident in the current International Residential Code, a document of over 900 pages that's continually increasing in specificity, complexity, and sheer mass. From a builder's perspective, compliance with this standard is a moving target that just keeps getting harder to hit. So, are building codes good or bad? Well, codes are good, of course. They enhance public safety by ensuring that builders use appropriate materials and methods. They reduce overall construction costs by eliminating the need to hire professional engineers to design standard buildings. They provide a mechanism for managing ever-increasing complexity in the construction industry. And, as we'll see later, they also provide a means of motivating builders toward long-term societal goals, like greater sustainability, which they might not pursue otherwise. No, codes are bad. They limit builders' flexibility, inhibit innovation, and create incentives for the proliferation of bland, dull, look-alike homes. They increase construction costs through excessively prescriptive requirements, many of which are unrelated to public safety. And they tend to foster a bureaucratic emphasis on compliance rather than reliance on the professional judgment of designers and builders. Well, as you might guess, both of these claims contain elements of truth. But for our purposes, it's most important simply to recognize that codes are a fact of life in our modern, technology-intensive world. And in myriad ways, codes determine the character of your home, its design as an engineered system, and its integration within the civil infrastructure that surrounds us. So it's in our best interest to understand what they are and how they work. In the next lecture, we'll take a closer look at one of the most important manifestations of modern building codes, the design of your house for structural load carrying.